Welcome to AI Paper Podcasts. Today's paper is OmniXtreme, Breaking the Generality Barrier in High Dynamic Humanoid Control. Getting a humanoid robot to do a backflip or a breakdance routine is hard. Getting a single AI model to do dozens of these extreme motions usually breaks the model completely.
A problem researchers call the generality barrier, or the fidelity scalability trade-off.
And the paper introduces OmniXtreme, a massive leap forward that splits the solution into two stages.
Stage 1 beats the learning bottleneck by ditching standard multi-motion reinforcement learning, which suffers from gradient interference.
Instead, it uses a flow-matching generative policy to distill diverse expert motions into one unified model.
Then Stage 2 bridges the sim-to-real gap using a residual RL policy that enforces hardcore real-world actuation constraints.
Things like torque evade limits and power-safe regularization to stop the robot from overloading its own motors via regenerative braking.
The result is a single, completely onboard policy running on a Unitree G1 robot performing flips, acrobatics, and martial arts with over 90% real-world success rate.
Okay, let's unpack this, because if you are an ML engineer or a researcher who has spent any time tuning reward functions for physical control policies, this paper targets a pain point, all too well. We have seen incredible progress recently in getting policies to track individual, highly dynamic motions.
But the moment you try to scale that up,
Right, like trying to train on the full fan on one data set or trying to merge multiple distinct movement styles into a single brain, the controllers they tend to become conservative.
yeah, they literally average out their behaviors or flat out fail on highly dynamic movements.
Which is obviously the exact opposite of what you want for acrobatic movements. If you average out a backflip and a forward roll, you just get a robot that falls flat on its face.
Exactly. And the authors of OmniXtreme realized they were fighting a two-front war here. The first front is what they define as the learning bottleneck, and this happens purely in the simulation phase.
Where standard MLP actors really struggle to map heterogeneous action targets.
Right. When you try to train a unified policy across many motions using multi-motion RL, you get severe gradient interference. The network updates required to perfect a back handspring directly fight the network updates needed to balance a slow, methodical martial arts pose.
Because the weights are being pulled in opposite directions.
Yeah, which leads to that conservative averaging. And then you have the second bottleneck, which is the physical executability bottleneck at deployment. Simulators by nature oversimplify actuators.
They ignore a lot of real-world physics.
They ignore torque speed limits, back electromotive force,
and power-related effects, right? Like regenerative braking.
Precisely.
Right.
Which will absolutely destroy the robot's stability in the real world.
So to fix this, OmniXtreme uses that two-stage framework we mentioned. Let's look at stage 1, scalable, flow-based pre-training. They use dataset aggregation.
Dagger-based distillation, right?
Yes, dagger-based distillation to train a flow-matching generative model.
So first, they train specific proximal policy optimization, or PPO, expert policies on individual motions.
Meaning you have a specialist for the flip, a specialist for the kick, a specialist for the breakdancing flare.
Exactly. Then they distill all of those experts into one unified flow matching policy.
So instead of standard MLPs or RL.
What's fascinating here is why they use flow matching instead of standard MLPs or RL. It actually decouples representation learning from the optimization process.
How does that work in practice?
Well, by learning a velocity field to denoise actions, the model capacity can scale massively without suffering from that nasty gradient interference of multi-motion RL.
Because it's not trying to optimize competing physical actions directly.
Right, it learns the flow. And the technical specifics to pull this off are wild. The architecture uses a transformer encoder just to process the 15-step history.
Which maps observations like joint states and the 6D torso orientation.
To a 1024-dimensional embedding, yeah. And then that massive embedding is fed into a deep MLP with hidden dimensions of 2048, 2048, and 2048.
That is a staggering amount of capacity.
But it needs it just to predict the velocity field for the denoising steps. It allows the model to absorb all those heterogeneous expert behaviors without averaging them out.
Here's where it gets really interesting. How do we prevent this highly capable simulated policy from breaking a physical robot?
That brings us to stage 2, actuation-aware post-training. They take that massive flow-matching base policy and they freeze it
Completely locked. The weights do not change.
completely. And then a lightweight MLP residual policy is trained on top of it, using RL to produce corrective actions.
And this phase relies on some hardcore actuation-aware modeling, like aggressive domain randomization.
Very aggressive. They increase the noise ranges by up to 50% for friction, mass, and delay.
Making the simulated environment incredibly hostile. But crucially, they relax the termination thresholds, right?
Yes, meaning they allow 1.5 times more orientation error before resetting the episode. So the residual policy learns to recover from near-catastrophic states rather than just giving up.
Which builds resilience. If you trip in the real world, the universe doesn't reset you. But what about the power limits?
That is the power-safe actuation regularization, which is vital for dynamic motions. High-speed impacts cause aggressive motor braking.
Because the robot has to rapidly decelerate its own mass.
Exactly. And that sends a massive surge of power back into the system. It turns into regenerative braking.
Which is terrible for the hardware.
It is. So the researchers explicitly penalize excessive negative joint mechanical power beyond a deadband threshold.
Focusing specifically on the knee joints.
Right, to prevent thermal stress or triggering the overcurrent protection, which would stop the robot from overloading its own motors and just shutting down midair.
They also tackle the torque speed curve here, too.
By replacing simple torque clipping with an admissible region that drops as joint velocity increases. This accounts for real-world nonlinear friction and internal losses.
And all of this was deployed on the actual hardware, the Unitree G1 Humanoid.
The computational achievement here is just incredible. There is no off-board compute.
None at all.
None. The entire pipeline, the forward kinematics, the flow-matching base policy using 5 ODE integration steps, and the residual policy, it's all executed entirely on board the Jetson Orient NX.
Which sounds like a latency nightmare. How fast is that actually running?
They optimized everything with TensorArt, achieving a blazing fast 10 millisecond inference latency.
Wow.
Yeah, it runs at a rock-solid 50 hertz in the real world.
Which it absolutely needs to pull off these moves. They push the system to the limit, testing a curated library of 60 highly challenging motions called extreme emotion.
Sourced from databases like AIM-SS and MimicKit.
We are talking back handsprings with twists, Thomas flares, forward rolls, and butterfly kicks.
And the quantitative victories of the simulation scaling tests are very clear. From scratch RL success rates collapsed to 73.9% as the library grew to 50 extreme motions.
Because the gradient interference just overwhelmed the network.
Exactly. But OmniXtreme maintained over a 95% success rate across all 50 motions.
And in the real-world deployment.
Out of 157 physical attempts across 24 extreme motions, the Unitree G1 achieved a 91.08% success rate.
So what does this all mean when we look at the specific hardware ablations? If you start stripping parts of that residual policy away, what actually causes the robot to fail?
It is super revealing.
Yeah.
For highly impulsive motions like flips, they just needed the torque speed motor constraints to work.
But what about contact-rich moves like breakdancing?
Those required the aggressive domain randomization to handle timing-sensitive perturbations.
Because transferring weight constantly is so sensitive to tiny errors and the high-impact acrobatics.
It consistently failed without the power safety regularization. The transient braking loads literally forced the robot into overcurrent protection shutdowns.
The massive takeaway for ML engineers and researchers listening is that the fidelity-scalability trade-off in humanoid control is not an unavoidable law of physics.
It is just a byproduct of outdated training paradigms.
Exactly. By combining generative representations like flow matching with hardcore actuation-aware physics modeling, we can put massive motion libraries onto single, real-time edge devices.
It leaves us with a lingering thought to mull over, actually. The authors noted that future generalization will require modeling even deeper hardware traits, like battery voltage dynamics under load.
Because as a battery drains, the motor's physical capabilities change.
Right. If we can successfully distill 60 extreme physical skills like martial arts and acrobatics into a single policy by treating physical control as a flow-matching generative problem, what happens when we apply this to thousands of everyday, subtle human tasks?
That is the big question.
Are we approaching a GPT moment for physical embodiment, where the bottleneck is no longer the AI learning algorithm, but simply the physical limits of the motors and batteries themselves?
Leaving you at that to explore on your own, dive into the research, and we will catch you on the next deep dive.